graph with no simple circuits is called a tree. Connected the graphs with no simple circuits is called a tree. So when we define paths, we define simple paths as those paths in which no edge is used more than once. So this then also applies to simple circuits, right? The circuit is simple if no edge is used more than one time. So here's an example of a simple circuit. A, B, C, E. So this is a simple circuit. And if you remove this condition of simplicity, then whenever you have an edge, you always have a non-simple circuit. Right? For example, the closed path, the circuit ABA, like when I go from A to B and then come back using the same edge, that's a non-simple circuit. So such non-simple circuits always exist, right, if your graph has at least one edge. But graphs with no simple circuits, right, so they have special significance, they're called trees. So I'm going to introduce some terminology now, and then we'll give you a few examples of trees. A marked point on a tree is called a root. And any vertex can be a root, but usually depends on the context. You'll see on the examples later that usually there's a natural choice for that special vertex. Marked vertex on a tree is called a root. And in mathematics, one draws trees from the root downwards, right? Not like in real life when trees go upwards. So this vertex is the root. Then other vertices are connected by edges to it. And first we draw all the vertices which are connected to the root vertex by a single edge. There can be several of them. And all of these vertices are called first level descendants. First level then to this new first level vertices we add further vertices, right? Those which would be connected to the root by a path of length 2. Right, so look something like this. And this gives you the second level descendants. This group of vertices is the second level descendants. And then I can continue drawing my tree, right? Next, I touch more vertices, right? Those would be all the vertices connected to the root by paths of length 3, right? Those constitute the third level descendant and so on, right? So third level and so on. tree. And another terminology which is often used is in this way of drawing. If you have a vertex at some level and it's connected to some other vertex at a lower level by a single edge, then, or it can be connected to several of those, then we say that the vertex above is the parent vertex, and all the vertices below are children. So in terms of the choice of terminology, it's like a mix of, the terminology used for family trees, where you have, vertices are humans, and they have children, descendants, right? And botanics terminology like roots, leaves, right? So next I will explain what the leaf is. A vertex of degree 1 that is different from the root is called a leaf. Alternatively, you can say a leaf is a vertex which has no children. Equivalently, a leaf is a vertex that has no children. All other vertices, including the root, are called internal vertices. All other vertices, including the root, are called the internal vertices. In the tree I've drawn here, assuming that's the whole tree, right? I can mark the leaves by circling them with a blue color. Right, so those leaves which have no children, those vertices which have no children, and they can be located at any level. Right, so those are leaves. Such vertices just surrounded by blue circles are leaves. Sorry. Right? It's the correct spelling. Sorry, sometimes I'm not very certain. So the rest of the vertices are the internal vertices, which I have not circled with blue, but those are internal vertices. All right, so let's look at some examples. Trees. And one which is common in history is a family tree. So humans correspond to vertices, or it could be, well, depending on the style, the vertex could be representing a couple, and then their children would be the corresponding children vertices, right? And typically such trees have a root, so that would be the oldest person in that family, the oldest known person in that family from which all other children descend. That would be the root. Okay. Files in a computer system, they're organized into a tree. Files in a computer system organized into a tree, and then there is a root directory which plays the role of the root. It's the root. Let's see. Imagine drawing each time you travel from folder to folder on your laptop, you're actually traveling through, if you start from the root directory, you're traveling along a tree. And there is a good reason why it's not just any graph, it's a tree. Because tree, as I'll explain in more detail soon, has a very special property that there is a unique path between any two vertices in a tree. So that organizes things in a certain way, right? For example, often if you install a new software in some directory, right, you need to put in a path to that directory, and that's a unique path from the root directory of how you can get there. Different example from pure mathematics, brackets in a mathematical formula if that formula is written correctly, they form a tree. Okay, let me explain this on a concrete example. Imagine that I had a mathematical formula with lots of symbols in it and lots of pairs of brackets. And then imagine that I erased all the symbols except for the brackets. So I will be using different types of brackets, like square, curly brackets, round brackets, but just for visibility, right? So it's easier to pair them up. It won't play any special significance which style I choose. So I may end up with something like this. Often, it can be a mathematical formula, or it could be also some computer code. Codes include just pairs of brackets, and the modern compilers, they always remind you if you forget to close the bracket, right? And then it's always aware of which left bracket is paired with which right bracket. So this has to be a consistent system. So how can I assign a tree to it? So to each pair of brackets, left and right, we assign a vertex. To each pair of brackets, we assign a vertex. And then two vertices would be linked by an edge if one pair sits inside the other pair with no intermediate pairs of brackets. So they are linked by an edge if one pair is inside the other pair, is inside the other pair with no enclosing intermediate pairs of brackets. And I can assign the outside, the largest pair of brackets inside which all others are contained. I can choose this as a root. And so this tree, it can be, so this root is easily identifiable. But I can also identify pairs of brackets which do not contain any other pairs of brackets inside them. Those correspond to the leaves. For example, the round brackets here, and the innermost pair of the round brackets over there, those don't contain any other pairs inside them, so those are leaves. So I can draw my tree either from the root downwards, or, because that's easily identifiable, or I can draw it from the leaves growing upwards. Okay, for that particular system, if I start from the root, so that the root is the square pair of brackets, and then inside it, I have the two pairs of the curly brackets, and there's nothing else there, so I link those, so I create two more vertices, which correspond to the pairs of the curly brackets, and I link them by the edges to the square brackets. Okay? Then the left pair of the curly brackets, it contains two pairs of the round brackets, right? So that gives me two more vertices in my tree. And the right pair of the curly brackets, it contains two pairs, but those are nested together, so they appear like this. The first pair of the round brackets, which immediately sits inside the curly brackets, and then beside it, there's another pair. So that's linked further on. Okay. So part of the checking syntaxes of correct formulae or correct codes involves actually constructing such trees and then checking that everything fits together correctly. Okay, another example, that will be my example 4, is the binary search tree. Binary search tree. So it's a tree in which each vertex is either a leaf or it contains two, not more than two children. So not more than two children are allowed. That's what the word binary signifies in this name. And in such binary search trees, each vertex is equipped with a numerical label. Each vertex is equipped with a numerical label. And the following important property holds that from any vertex you can go left or right. So suppose the label for this vertex is capital L, and it can have one descendant, but typically I will have one descendant, 0, or two descendants. Right? So if there are two descendants, then the rule is that when you go left, then for all vertices you can reach further down, the values of the labels should be smaller than the label L. And when you go right, then for all vertices, you will reach down below, the values of these labels should be greater than the label L. So when you go left, you get labels smaller, and then capital L. When you go right, you get labels greater than L. Let me draw a concrete example. In this example, I'll put these numerical labels instead of vertices. A concrete example of a binary search tree. So 38 is the label for the root. And then there are two vertices linked on the left and on the right with the labels 14 and 56. Here we have 8, 23, 18, 20, and I always go left or right. Sometimes I only go left, or I only go right, but I always respect the rule that the label will get smaller if I go left, and will get greater if I go right. So you can check, right? In this small tree, this rule is always satisfied. So if you have such a tree, it's convenient to use it to store objects. Again, you can think of it, say, as a directory system or file system on a computer, or some other database which is simply organized in terms of a tree. And you can think that there are objects stored at each vertex. So objects are stored at each vertex, any kind of object, some information. And then, suppose you get a request, find in this tree the vertex which stores an object with a given label. So to find a vertex with a given label, call that label M, right where an object is stored, which we want to find. I would say where is the object is stored that we want to find. We start from the root, and we start traveling along the tree, always comparing the label of the vertex to the label of the object we want to find. And if that label happens to be greater than the label M, then we go left. We descend down by the left edge. If it happens to be greater than If M happens to be greater than the label of the vertex, then we go right. Okay, let me write this down. So we start from the root and travel along the tree, following the rule. If the label of the vertex L is greater than M, right, then go left. And then if L is smaller than M, then go right. Well, if the object is sitting somewhere in the tree, you will find it by, eventually you will get it. Was this construction mentioned in any of the data science courses that CS students? Data structure course, yes, it was. Okay, so it's familiar to you, but I guess from us students, that's something probably new. Right, so there are some examples of trees. So next I want to introduce some special types of trees and give you more terminology, and then discuss in more detail the basic properties of trees. So some special trees. I already mentioned binary trees. The binary trees is a tree in which each vertex has less or equal than 2 descendants. So each vertex has less or equal than 2 children. And if you're allowed to have 0 children or precisely 2 children, then and this is called a full binary tree. Full binary trees are 0 or 2 children. So let me draw the examples. So here's an example of a binary tree which is not a full binary tree. So basically, whenever you have vertices with degree 2, right, they'll spoil this property. They will have exactly one descendant. So this is a binary tree which is not full. Here's an example of a full binary tree. So here, you either don't draw any lines downwards, and then you have a leaf, or you draw precisely 2 lines downwards, 2 edges. Okay. So this is a full example of a full binary tree. You can also introduce ternary trees for which each vertex has less or equal than 3 children, and full ternary trees where you have either 0 or exactly 3 children. So ternary trees less or equal than 3 children, and full ternary zero or 3 children. Okay, and this generalizes to, well, I can only use Latin up to 4 children. Quaternary is the name for less or equal than 4 children. And I don't know, maybe there's something Latin, but I will simply say n-ary trees. Quaternary maybe. So n-ary trees for which every vertex has less or equal than n children, and full n-ary where each vertex has 0 or n, or exactly n children. Okay, so in some problems we will be dealing with this type of trees, with this special property. Another notion which I will be using is that of a forest. It's another piece of terminology which comes from botanics. Forest is a graph for which each connected component is a tree. Is a graph disconnected, right? For which each connected component is a tree. And it does really look like a bunch of trees growing downwards. Here's an example. this is a tree, this is a forest graph with 3 trees. This is a forest with 3 trees. All right. So let's next discuss the special properties of trees. So we'll formulate this as a theorem which lists two properties, each of which can be used as an alternative definition of a tree. G is a tree if and only if either one of the 2 properties holds, and the first one, property A, is any 2 vertices are connected by exactly one single path. Any 2 vertices in G are connected by exactly one simple path. There's this property, which is the key property for the usage in data structures. There's always a simple path to reach to the stored information. And property B, the graph is connected, but removing any edge leaves a disconnected graph. G is connected, but removing any edge a disconnected graph. So this is also a very important property for applications. If you want to build a network with a minimal number of connections, then but all nodes connected by at least one path to each other, then this network has to be organized into a tree. This property tells you that it has a minimal number of connections, right, to keep the whole graph connected. Remove any one edge, and it falls apart, right, into disconnected parts. So let me discuss how this theorem follows. It's not complicated. So I'll first prove that if I have a tree, then this implies property A. So if I have a connected graph with no simple circuits, that was my definition of what a tree is, then any 2 vertices in G are connected by exactly one simple path. So I assume I have a tree, then assume we have 2 different paths. So assume there are 2 different simple paths between a pair of vertices, call them A and B. Well, then if I draw it, there's one path from A to B, and then if there's a different path, then the 2 of them form a circuit. Then a simple circuit could be formed. But since we're in a tree, this is not allowed, right? So this cannot happen. So if you have a tree, property A always holds. So next, then let's prove that property A implies property B. So assume that any two vertices in G are connected by exactly one simple path, then, well, then naturally follows that the graph is connected because at least one path is there. But moreover, remove any edge, you get a disconnected graph. So why A implies B? Well, any two adjacent vertices in G are connected, must be connected by a unique path, right, which is the edge AB. And these two vertices are AB, and AB is the unique path, right, by A. Well, but since it is unique, if you remove it from the graph, then there won't be any other path leading from A to B, and therefore it will become disconnected. Okay, so since it is unique, removing this edge leaves are disconnected graph. And finally, to close the logical loop of implications, let's assume that B holds and then prove that this graph must be a tree. And we will make a full circle and prove the full theorem. So we need to assume that the graph is connected, okay, which is part of the definition of the tree, and assume that removing any edge gives us a disconnected graph. Then we must show that there are no simple circuits. Well, suppose there was one, then clearly in that circuit, if you remove one edge from it, anywhere, it won't be disconnected because it only affects the two adjacent vertices, which were linked by that edge, but you can go around the circuit in the other direction to travel between this pair. Let me write this down. So finally, B implies G is a tree because if there was a simple circuit, we could, like this, we could remove any edge from it, keeping the graph connected. Because say if I remove this edge, then between this pair of vertices, I can still find a path going around the loop, around the rest of the loop. Okay, so all these three things, being a tree, having a property A, or having a property B, they're all equivalent. So sometimes they're taken as alternative definitions of what a tree is. There's another important property, which also can be served as a characteristic property of a tree, and it plays a special role because it's quantitative. So I will formulate as a theorem. a tree with n vertices has n minus 1 edges. Tree with n vertices has n minus 1 edges. Alternatively, you can write it using a different notation. So when we talked about graphs before, we used capital D for the set of vertices and capital E for the list of edges. So we can write this formula. So the number of edges is equal to the number of vertices minus 1. So why is this the case? Let's draw our tree as downwards from the root. And as I draw it, I will be labeling my edges and my new vertices. So first, I draw the level 1 descendants, right? And with each new level 1 descendant comes a new edge. So this new descendant, I'll number it as descendant 1, and this new edge is number 1 edge. Then I have descendant number 2, and then edge number 2, descendant number 3, edge number 3, and so on. Once I'm done drawing all level 1 descendants, I proceed by drawing level 2 descendants, and I use exactly the same labeling. I continue labeling them. So if I have descendants for the here, I will call this edge 4, vertex 4, edge 5, vertex 5. I don't care how they're linked. It's just with each new vertex, a new edge will come, or vice versa. With each new edge, a new vertex comes. And I keep numbering them as I draw them. 6, 6, 7, 7, and so on. Then it's clear there will be as many vertices as there are edges, except for the root, right? The root is the only one which didn't have any edge descending to it, so it didn't participate in the labeling at all. So this is one extra vertex, right? So if I remove the root from the number of vertices, I get exactly the number of edges. Right, so this labeling implies that there are as many edges as there are vertices minus the root. Okay. And moreover, if you have a connected graph for which this formula holds, then one can prove that it must be a tree. Okay. So here I will omit the proof, but just as a remark, a connected graph for which the number of edges equals the number of vertices minus 1 must be a tree. The proof is just a bit more involved. It's not complicated, but a bit more involved, so I'm not going to get it. Any questions so far? Okay, so this leads us already, this last result, which is a quantitative feature, actually gives us the opportunity to answer some counting questions. So I'll get started on one such problem. So I'll do a sequence of counting problems in trees. So counting problems. Trees. So here's one example. Find how many leaves are in a full quaternary tree with 300 edges. Find how many leaves are in a full four array or quaternary tree with the number of edges being 300. Right, so how to do this problem? I'll introduce some notation which I will also be using in other such counting problems. So let capital L stand for the number of leaves in this graph. The number of leaves, and let capital I be the number of the internal vertices. The number of internal vertices. Well then, the total number of vertices is L plus I. Right? And since we have a tree, the total number of vertices must be the number of edges plus 1. It's equals to the number of edges plus 1. And we're told that there are 300 edges, so this equals the total number of vertices is 301. Okay. So this we know, but we want to find, well, these vertices are split into leaves and internal vertices. And now we want to find which ones of these 301 vertices are leaves, how many of those are leaves. And here we will use the special properties, not just arbitrary tree, but it's a quaternary or four-array. So since we have quaternary or four-array tree, the number of edges is the number of internal vertices times 4. Because each internal vertex would have 4 children. Right? So in a full quaternary tree, we have 0 or 4 children, right, by definition. 0 means this is a leaf, and 4 means it's an internal vertex. Right? So, because each internal vertex has 4 children. So you can count all of the edges, because they all will emanate from internal vertices, right? And each one will emanate 4. So this is an internal vertex. We have 4 children, and therefore 4 new edges. So that holds. So if we substitute this now into our relation, so I is equal to E over 4, which is 300 divided by 4, and that's 75. So we have 75 internal vertices, and therefore, since the total number of vertices is 301, the number of leaves equals 301 minus the number of internal vertices, so it's 301 minus 75. And that gives us 226. That's the answer to this question. There is not much arithmetic here, not much calculations, right? But I want you to appreciate this result, because there are many such trees. Right? And in fact, I once did a similar problem on a meter, and I had a student who just drew one, completely attaching the vertices at random. So whichever tree you draw, whichever quaternary tree you draw, with 300 edges, right, will have this number of leaves. So that student drew a huge tree and then counted the leaves, right? So I accepted it as a partial, answer to the question, and then I give the numbers in thousands. So that's not a solution, but I just wanted to appreciate, right, the counting